All right, welcome back, folks, to another session of Engineering 260. Today, we're going to look into the transistor. This is our first introduction to a fundamental amplifying device that is something that can take a small signal or a small electric voltage or current, in this case, a small current, and turn it into a much bigger current and amplify really the power of of a signal. So one kind of transistor type is called the bipolar junction transistor, or BJT for short. The transistor itself it can look like any of these packages down here. So when you're working with them in the lab, you might see things that look like this. Here's a common one. It's a 3-terminal device, so that's actually different than any of the other components we've looked at so far in terms of resistors or capacitors or inductors. Even voltage and current sources, those are all 2-terminal devices. This is a 3-terminal device, and the terminals are the collector, the base, and the emitter. And this is the schematic symbol shown for it over here. Now, what you have with this device is that you always have there's 3 currents that come in and out of the device. There's the base current, IB. There's the collector current, IC, and there's the emitter current, IE. And by KCL, you always have that the sum of the currents in and out of this junction. It's a 3-terminal device, and the sum of the currents in and out of them, you will always have that they equal 0. So the base current and the collector current are both into the junction, pointing into the junction. And the emitter current is pointing out of the junction. So we can just move it over onto the other side. So the base current plus the emitter current, plus the collector current is equal to the emitter current. Let's just point out the fact that you can always tell which one's the emitter because it has this arrow pointing out of it like that. That arrow also tells you the direction of the current flow, that it comes into the base and then out of the emitter. Now, what's so special about this device is that when you put in a little bit of base current, let's say this was on the order of 10 microamps or something like that, okay? Now this current could be really small. The magic thing about a transistor is that the resulting current flow through the collector, from the collector, is super, super big. IC could be on the order of maybe 1 milliamp all the way up to 10 amps. Well, maybe that's a little bit high. Maybe we'll say like up to an amp or something like that. Okay. And this is really big, and it turns out that that's the magic thing that that a transistor does, is that it amplifies the base current. In fact, the BJT current gain is this parameter called beta. And what you have is that the collector current is always beta times bigger than the base current, where beta is often in the range of maybe like 50 up to 200 for many many typical bipolar junction transistors. So there's that aspect. Now so the bipolar junction transistor, or BJT, amplifies a small current going into the base, a little bit of trickle current, 10 microamps or something, not very much, and it can turn that into a much bigger current. What is that useful for? Well, if you wanted to create an amplifier that takes a really small signal out of a microphone and then drives a really big signal out of a speaker, and that speaker is moving much more energy because it's a much larger mechanical device, you need something to amplify the power on the way. Another example, in a motor control, for example, you want to take a weak little signal out of a computer that might be able to drive, an Arduino or microcontroller that could drive 30 milliamps into a device. Well, 30 milliamps isn't enough to turn very many motors at all. Many motors need, more on the order of amps and even hundreds of amps for some very large electric motors. So what do you put between the Arduino or microcontroller or microcomputer and the motor? You stick some kind of amplifying device or amplifying network. It's made of a transistor or multiple transistors. So a couple of other parameters here. Let's just talk about how do you, so the voltage between the collector and the emitter is one of the parameters. We call that VCE. Turns out that that determines how the device operates. We're not going to talk about this so much in this class. You will if you go and take further courses in electronics. We will talk about the base to emitter voltage, VBE, the voltage at the base to the voltage at the emitter. It turns out to turn on the BJT, you can go much more into this, but essentially you need that VBE is equal to or greater than 0.7 volts. And for a lot of our calculations, we'll just assume that it's 0.7 volts. It turns out because of the nature of silicon PN junctions, which is what the base and emitter is made out of, P-type material and N-type material, silicon. It generally saturates at about 0.7 volts once you put some current into there. So we'll just assume that in our calculations, and we'll show that on the next page. Let's talk about some of the other parameters or effects of the fact that by this KCL, by the fact that the base and collector currents point into the junction and the emitter is coming out. So the base plus the collector current is equal to the emitter current. Now remember, the base current is really small. The collector current is really big. And essentially, the emitter current is really big also. It's just slightly bigger than the collector current because it's the collector current plus this small little extra bit of base current. But if the base current is 10 microamps and the collector current is 1 milliamp, then that's not very much of a change, right? So if that were the case, you'd have, something like 10 microamps plus 1 milliamp would equal 1.01 milliamps. So you can see that the emitter current isn't very much bigger than the collector current. And a lot of times in many calculations, people will just assume that the emitter current is the same value as the collector current. So let's then take a look at one of the other ways that you can relate the emitter and base currents by the fact that the collector current, this guy here, is equal to the beta times IB. So actually, if we write the collector current in terms of beta IB, whoops, hang on here, beta IB, that is equal to the emitter current. We could write this as IB times beta plus 1 IE. We're just pulling out the base current term there. I didn't draw that very well. I'll try to do that a little bit better there. There we go. The base current. And so that relates the base current and the emitter current directly. If you wanted to solve for the emitter current, or rather if you wanted to solve for the base current, if you knew the emitter current, which we'll see on the next slide, you could solve for it that way. The base current is just the emitter current divided by beta plus 1. It's scaled by that.